So this presentation is on a project that I've been working on over the past year or so with my mentor Yoshi Phillip, and we've been working on creating profiles for HPC jobs using time series data and generating statistical expectations for a job's behavior using past job runs of that same job type. So just to distinguish what we mean by job profiling from where you may have heard that term used before, this isn't actually an embedded library for tracking code through function calls. Instead, we're creating a profile based on a job's use of machine resources, such as CPU load, memory, and bandwidth. So a job profile consists of a combination of both top-level job attributes, like the job's name, start time, end time, that sort of thing, with the metric time series data that I was just describing. And we're not just looking at the raw time series data for each node, but we're also aggregating that data across all the nodes at each point in time. So for example, looking at the average load value at each time point across all the nodes. So here's an example of how you could display a job's profile and its data through a web page. At the top of the page we have some of the top level job attributes, and then we've decided to separate out the head node series from the compute nodes with the first four graphs showing different metrics across time for the head node. And then in the compute nodes you can actually see different ways of visualizing these, what's usually multiple nodes. Like in the graph on the far left, you can see an average series and then the minimum and maximum series as these dotted lines. Or you could just display each compute node series individually and hover over different series to highlight individual nodes. So you might be wondering what this kind of purple cloud is in the background, and that's actually the job's expectation. So a job's expectation basically consists of a statistical summary of past successful job runs, like the average and standard deviation of those past jobs. And you can use this to visualize a kind of cloud path where the center of the path is the average of the previous jobs and the height is showing you the standard deviations from that average. So in this example that we've created, just using mock data in this case, this job is deviating more than 2 standard deviations from its expectation for this period of time, at least with a memory metric, which makes you wonder if maybe something anomalous happened at that point. But next I'd like to look at an actual real-world use case. So in this example, we have a job where the load values have basically dropped down to 0 towards the end of that job and clearly fallen outside of its expectation cloud. But I wanted to show you another way that you can visualize actually multiple jobs and compare one job to other jobs that may be of the same type or in the same expectation. So here on the left, we've created a kind of color map where each of these horizontal bars represents a different job, and the load value across time is represented with different colors. So for example, this job corresponds to this horizontal bar where you can see the load values have dropped down to basically 0 with this purple color at the end. You can also see some other jobs where there's missing data towards the end, and this job at the bottom where the loads drop down to 0 for the vast majority of that job's wall clock time. So this brings up an important use case where you can see how it would be really valuable to detect when a job's dropping outside of its expectation and just, in this example, kind of idling, and be able to cancel that job well before wall clock termination using this kind of actionable information. I should also note that in addition to creating these visualizations for detecting anomalies, we've also created some automated processes for mathematically detecting anomalies and then using a kind of dashboard to bring those anomalies to the user's attention so they can then investigate further. So you can see in this example that this particular job type has a fair amount of noise over the course of the job, which is then reflected in the kind of broad expectation cloud. But we also came across quite a few jobs or job types that were much more consistent. Like as you can see in these two sets of jobs, each job run is almost identical to the others, and this allows you to create a really narrow expectation and really easily see when a job's deviating from that expectation. So that could be useful for something like a benchmark job that's supposed to be the exact same thing each time, and then you might pick up on something, you know, maybe that's happening on the system that interferes with that normal course. So here's another example where each job run is highly consistent with just about the same load value throughout the entire course of the job, except for these kind of interesting blips where the load value seems to deviate for a brief period of time. But interestingly, that blip seemed to occur in different spots on different job runs, and we suspected that maybe this was just something happening at a particular point in time. So we decided to shift the jobs according to their start time, and it turned out that that blip suddenly lined up for every job. So kind of supporting our hypothesis that maybe there's something occurring on the system at that time that was just affecting all of the jobs. So after discovering that one example of what looked like a system-wide kind of blip, we decided to look through the data for other examples, and even looking across multiple users and multiple job types to see if there's anything affecting really the whole system at a point in time. And here you can see there's actually like 3 different kinds of disruptions on the system, where there seems to be some missing data here, missing data interspersed with high load here, and then just a really brief blip in the system there. And we actually found quite a few of these kind of events, system-wide events across the course of the day, day's worth of data that we were working with. Here's one other example where it seems to be more of a kind of storm on the system than just a little blip with high load and missing data. And it seems to have, you know, maybe even led to the termination of some of these different jobs that started at the different times, but all seem to basically terminate at the same time. So it's definitely, you can see the utility of being able to scan through the system data and visualize this kind of thing. And recently we've been working on creating some really larger scale visualizations for looking at, say, all of the jobs over the course of an entire day, all in one visualization. So one thought that may have already occurred to you is that jobs aren't always grouped neatly into workload types, and so you may not know which jobs actually belong to a particular expectation. And even when they are labeled, that labeling may be incorrect. So we've decided to develop a machine learning technique for classifying different types of jobs based on their time series data. Unfortunately, I don't have the time to go into the details of our technique and experiment, but here's the results, where you can see that we've taken each individual job and encoded it into a 2-dimensional vector. Those vectors grouped neatly into 3 different clusters, with both the training and test data overlapping in those clusters, where each cluster corresponds to a distinct job type. And here you can see how those 2-dimensional job encodings can be then fed back into the decoder portion of the autoencoder to produce a series that resembles the original job series. So the original job series is displayed as this orange line, and the decoding is displayed as the blue line. So finally, here's a few different use cases for our techniques. We have system benchmarking, resource scheduling, system utilization and planning, and finally log analytics. So that's basically what we've been working on. Thanks for checking out this presentation.